We study the motion of a charged particle influenced by the Newtonian gravity of a point mass, all immersed in a uniform magnetic field. This can serve as a toy model for astrophysical jets. We express the equations of motion in cylindrical coordinates with polar radius r, height z, spherical radius R, and polar angle theta. Its Hamiltonian contains two constants of motion, an angular momentum L and a total energy h. Notice how it is also independent of theta. What this implies is that the system can be studied with just r and z, meaning that we can ignore all angular motion of the particle. We can treat the Hamiltonian like an energy equation, with the total energy h, a kinetic energy, and the potential energy. When we set the kinetic energy as 0, we get what we call a zero velocity curve. When a particle touches this curve, it will have a zero velocity, hence the name. So these curves dictate the trajectory boundaries in the system. The shape of these curves is defined by L and, more importantly, h. It shrinks when the energy is decreased, and it expands when it is increased. Higher h will eventually reach a point where the curve will open towards the infinities of z, and now have two vertical asymptotes shown in red, which we call the asymptotes of escape. They are called as such because their existence now allows some trajectories to escape towards the infinities of z. The main tool for analysis we used are Poincare plots. Every time a trajectory touches z equals 0, we get the position and velocity at that exact moment along r, and plot it in the Poincare plot. We can do this not only for a single trajectory. It can be done for tens and hundreds of trajectories. This is the power of the Poincare plots. It allows us to study several trajectories all at the same time within a single plot, and over time, some patterns will emerge in the Poincare plot, and this will be the basis for classifying different trajectories in the system. Now, what are these classifications? And how do they depend on the constants of motion? And can we rigidly analyze escaping trajectories? This and more can be answered by my thesis and during my thesis defense. See you!